Hello, everyone. Hello, everyone. Thank you for this webinar series. I'm Jian Ting from Shanghai Jiao Tong University. This webinar series is the title of this webinar series is Risk, Resilience, and Sustainability Informed Integrated Management of Infrastructure Systems. Actually, probably you already know it's jointly organized by JCSS, Joint Committee on Structural Safety, Global Consensus, Joint Committee on Global Consensus, and International Davos, this Risk Forum, and Harbin Institute of Technology, HIT, and Shanghai Jiao Tong University, and Aalborg University. Actually, today, it's my honor to host this talk held spoke by this Professor Eleni Katsi from ETH Zurich. The title of this talk is Robust Dynamical Systems Monitoring, Learning by Modeling. Before Professor Katsi's talk, I would like to take 1 minute to introduce her. I'm sure that all of us, or most of us, already know Professor Katsi very well. Actually, Professor Katsi is the Chair Professor of Structural Mechanics and Monitoring at the Department of Civil, Environmental, and Geomatic Engineering of ETH Zurich, actually the bulk of ETH Zurich. Actually, I knew Professor Katsi around, I think, 12 years ago when she just moved to ETH Zurich as a professor, when I was still striving for my PhD doctoral degree. And as I remember, she sets a record in ETH Zurich that she is the youngest professor of ETH Zurich in the history. And her research interests include the fields of structural health monitoring and structural dynamics, nonlinear system identification, and intelligent life cycle assessment for engineered systems. She has authored more than 300 papers in peer-reviewed journals and conference proceedings, and further serves as an editor for international journals. Actually, I think many journals like MSSP or other journals she is the editors on the editor board in the domains of dynamics and SHM. She recently led the ERC starting grant Windmill on the topic of smart monitoring, inspection, and the life cycle assessment of wind turbines. And just this ERC starting grant just finished recently. And her work in the domain of self-aware infrastructure was recognized by this ASCE, American Society of Civil Engineers. And she got this Walter Huber Research Prize in the year 2020. Yeah. Thank you, and Professor Katsi, thank you for your time.
Thank you very much, Angel. It's very nice to see you again after, we have met each other also more recently, but it's nice to see your evolution since 2010. And thank you for inviting me in this webinar series. So maybe I will start right away. Let me know if you can see the screen.
Yes.
Should be the full screen,
yes.
Right? Okay, great.
Yeah.
So, as the title of my talk reflects, today I would like to discuss the aspects of monitoring, but in tandem with the element of simulation, which will hold perhaps the largest part of this talk. But before I go about the elaboration on the fusion of these two concepts, I will start with the definition of the main of the structural health monitoring chain, which comprises a series of different links, starting from the acquisition of data, which today we know can be accomplished with different means, and on large-scale structural systems. There exists a variety of technologies that can acquire information such as strain, displacements, accelerations, environmental information, force-related information on systems at an increasingly lower cost. So in my group, we do not work on the development of the hardware, of course, but we do work on the optimal processing of the information that comes from different types of such systems, with the goal of developing indicators of the performance of these systems in terms of diagnostic and prognostic capabilities, in terms of assessing or eventually supporting the decisions that relate to such structural systems. But a main feature of the research pursued in our group is the coupling of these indicators that can be data-driven with aspects that relate to first principles, and specifically models that draw from principles of mechanics and dynamics. I will return to this focus in the next few slides, but let me also complete the chain by saying that ultimately we would like to be able to extract indicators that are meaningful and interpretable, and that can be used for assessment not only at the individual structural level, but also at the system level. And when I discuss a system, or sometimes when we refer to a population or a fleet, we are actually referring to conglomerates or assemblies of different structures. You can imagine a roadway system comprising different components such as bridges and tunnels, or even populations of structures such as wind farms comprised of different turbines. So how do we reach these different levels of SHM? I will attempt to describe the process that we follow in my group, and I will focus on this element of simulation, which is really what we use as a booster to learning, hence the title of this talk. Before I proceed with some use cases, I think it's useful to explain that structural health monitoring, of course, is not only related to civil structures. And I say this because oftentimes this is a misconception, so given that I'm actually situated in the civil engineering department, but we can monitor different types of systems. And in fact, in my group, we're doing this actively on a variety of structures, from railway and transport infrastructure, where we use sensors both on the infrastructure as well as on vehicles. On wind energy systems, as Janjun mentioned, we had the NERC starting grant for a number of years that has really increased the activities that we have in this domain. Conventional civil infrastructure, such as bridges and buildings that we monitor under demolition, but of course also industrial assets such as bearings, anchors, and other elements that are also, in a sense, structures and that can be monitored, meaning that we can extract information from appropriately deployed sensors. Now, before I go into this main focus, that is the exploitation of modeling and simulation, I would like to also show you what we can do purely on the basis of data, which of course we know is possible or increasingly possible today. Data-driven or purely black box simulators can accomplish a lot. And we of course use them also for our purposes. Here I will show you an example from the domain of wind energy modeling, specifically for simulation of wake effects, where the main tool that we here utilize is a black box or purely data-driven model. So here you see a very popular image of this effect of wakes, which is basically the influence of forefront turbines to those that are in the shade, in the shadow of these turbines. And you see the wake phenomenon, which eventually also translates into a heavier or a more adverse loading of these systems, of these individual structures, depending on their placement within the farm. In order to reflect this phenomenon, actually a number of empirical models do exist. Also, it's possible to do more refined computational fluid dynamics simulations, but of course, the reality is never fully captured with these usually approximated models. So here is where the power of data can come in, and this is what we did. We utilized data from information of wind gathered at each and every of these turbines in the farm and tried to relate the loads, so quantities that relate to the fatiguing of these turbines or the wind deficit of these turbines, as it is called, on the basis of information from the mean wind speed and direction in the farm collected from a meteorological mast. We did this using a conditional variational autoencoder, which is a purely data-driven model. And in the end, we succeed in having a generative model that does not draw from physics or first principles, but is descriptive of the actual situation on the site. And this is where data can actually take us where models and approximations perhaps cannot. Nowhere in this process did we use mechanics or physics, but of course we cannot always get away with such a representation. I'm going to try to explain when this does not work. But before I do that, let me also show you another more conventional example of how we use data-driven models and indicators in the domain of monitoring. Again, I will use the example of a wind turbine, where we can assume that we have a set of sensors that generate information on the response of the system, typically vibration response for such dynamic structures, and where we use principles of dynamics, typically to develop data-driven models. For example, time series representations. There's a number of such representations that can be used because a wind turbine is a time-varying system. One possible representation is of the time-varying autoregressive type. Here, for example, you see a time-varying autoregressive model in the blue lines that appear on this contour plot that is fitted on the spectrogram, so on the actual data that originate from the accelerometers that are deployed on this system. Now, a challenge in these operating structures is that their response is actually also a function of the influencing parameters, meaning the environment, also operational variables, what is the rotor speed, for example, that are descriptive of a specific time window in which we collect data. In order to reflect this variability, a popular way to construct or to reflect this is to construct a dependence model. So, for example, in our case, the framework we have developed is to usually condition the coefficients of such time series representations on the environmental and operational variables, which act over a longer time period, for example, a period of a month. There's many different ways in which you can achieve this. And we have experimented with a few that you see here, including polynomial chaos expansions and Gaussian process regressions. But at the end of the day, the outcome of such a hierarchical model is to have a holistic model that can capture the dynamics of the turbine as it is monitored across its operating conditions, and which we can then use as a predictive model of the quantities that we measure. The reason why we do this is that by monitoring thereafter the discrepancy, we can extract these data-driven indicators, which already at this stage include some principles of dynamics, which are captured here in these time series representations. So if we look at how this operates, it would look a bit like this. So we collect, or we try to train this dependence model over a period of collected data, and then we use it in validation mode, where we have the error between what we predict and what is being measured. And then on the basis of tracking of this indicator, let's call it, we of course can monitor the outliers. We can also do this in a probabilistic way. We can utilize robust outlier analysis to understand which of these outliers are persistent. And in the end, we have the possibility to classify these outliers in this space where we have the response acting as expected. We issue, in this case, a normal operating condition. We have the violation of the outliers in regions of the inputs, meaning the acting environments and operational variables, in regions of these inputs that are well known, or our model has already been trained for these operating actions. In this case, we issue a red alarm, or we may have violation again of these thresholds of our trained space in regions where the inputs have not been observed before. So we have higher temperatures, we may have diverse wind speeds or wind direction, variables or ranges that have not been within our observed space. In this case, we issue what is called a yellow alarm. So you will notice that we're using this ragtime flagging, red, amber, green flagging system, which allows us to then deliver to the engineer indicators that are interpretable and do not contain a level of detail that is not also useful for their decision process. So we have this RAG flagging system. We also know that if we have a network of sensors, we can go a step further. So for example, here I'm showing you a distribution or the case of a bridge system. In fact, this is an actual bridge that we have controllably damaged in Switzerland, and where we tried to see whether the location of the different sensors, which are also heterogeneous in nature, we were using both acceleration and strain in this case, and we've seen, or we can prove, that actually the exploitation of the location of these sensors can also lead to the localization of damage. So we figured this out by understanding whether indeed the controlled damage could have been detected. And so we can do this. We can have a detection of damage, possibly a localization of damage, but in both of these cases, we're actually discussing diagnostic tasks. What we cannot achieve, or what I'm not showing you here, is what we would call a prognostic task. So the question, for example, of how longer can this bridge continue before it actually fails, or what is the expectation of fatigue accumulation in the future on the basis of its operation until now. And typically, this is where data is not enough. So this is where the aspect of modeling is of paramount importance. I will try to explain this here in this next few slides. So what I'm here trying to maintain is that purely data-driven representations are sufficient and have been shown to actually be very successful in the task of diagnosis, but they are not so adequate when we're trying to achieve a forecasting or prognostic task. And this is where physics-based representations can give us this power of extrapolation. And so in our group, since we're using monitoring, we always have to have data in the loop, and we opt for what is known as hybrid modeling, which is the synergy between the physics and the data, and which has to be achieved in a computationally efficient way, especially where to deliver what we call virtualizations or digital twins of structural systems, interactive digital models that can actually interact with the physical representation or the physical part of the twin, and be used for diagnostic and control tasks visibly in real time as data is obtained. In order to do this, the physics has to also be computationally affordable. So what I will show you here is how to achieve these hybrid representations. I will start with the first means to achieve a hybrid model, but first of all in a so-called offline manner. I will show you here an example from our AeroSense project, which is a project where we're developing a sensor, actually a sensing skin, which is a wrapper that is manufactured to understand erosion over a wind turbine blade. It's basically a system that contains acoustic and pressure sensors, and where we're trying to see whether the picking up of this information can also give us information about the evolution of this wearing effect or the erosion of the blades. One of the tasks that we're curious to do, and where we are using physics in the loop, is whether the collection of this pressure information on the airfoil might be used to reconstruct the loads or the flow around the blade. And to understand this, we have been using CFD, or computational fluid dynamics modeling. Here it is more in the static sense. So we're trying to reproduce the flow field around this airfoil by using as input or as a measurement the information that would come from such an AeroSense system. Pressure, namely pressure measurements here at this boundary. We're using a graph neural network, which is trained on the basis of the CFD models in this case, and which can be trained on specific airfoil architectures and eventually transferred to more random geometries. So in initial work, we have seen that it is possible to reconstruct to a certain degree the flow. Here you see the ground truth on top and the predicted information on the bottom. You see that we are not so successful mostly at the tails of the airfoil, but it seems that it is plausible, and it's also something that for us is encouraging, because it means that if we can generalize for different geometries, then it means that we can achieve transfer by using such a graph neural network-based representation. In this case, we're doing a fusion of the model and the data, but we're doing it in an offline manner because we have used the physics-based model primarily for training and it's essentially an emulator. What we achieve with the GNN is an emulator of the response. However, for a number of tasks, especially for those tasks that have to do with tracking, monitoring, diagnostics, and twinning, we have to have an interaction that is not offline, but rather acts in real time, meaning at every point in time as a dynamic acquisition takes place. And this is where hybrid modeling becomes more challenging. I'm showing you here this kind of a concept where we have an engineered system, which can be potentially nonlinear. We already discussed that usually our systems are operating under varying environmental and operational conditions, feasibly with distributed loads most of the time. We don't have very simplified point source loads, which would have made computation easier. And we would like to assimilate data into the predictions that come out of our modeling in real time. There's different tasks for which this is useful. I already mentioned digital twinning. I will show you examples with the so-called task of virtual sensing, how to predict the response of a system in unmeasured locations based on few and sparse observations. Indicators that we wish to develop that are also boosted from physics and have to, again, operate in real time if we care about diagnostic or control tasks. And of course, interactive twins, which can be used for decision support. This is a concept that we now are referring to as augmented twinning, where also the expert could come in the loop by having the visual from such predictive systems. So how to achieve this kind of real-time interaction? I will present to you perhaps the most common approach, or the one that we utilize in our group for achieving this task, primarily for the so-called task of virtual sensing. So let us take the example of a monitored structure, for example, a wing or a blade. These are systems that come from some of our recent projects, and that's why you see me often referring to such geometries, and where we can assume that we can have few sparse, usually distributed sensors on these systems. Oftentimes, these are accelerometers or strain gauges, and where we would like to understand or extract the response of the system in a way that optimally combines the physics that we know of, even if it is partial and erroneous to some degree, and the data that we collect. We would also like to get these predictions in the full field, as we say, so also in unmeasured locations. The way to achieve this is to use the concept of Bayesian filtering. So let me describe roughly what this means, assuming we have a structural system from which we have a number of sensors installed that extract an output in the form of measurements. We also assume that the system is operating under the influence of inputs that can be distributed and which are very frequently unknown. It is not very easy to measure loads that are acting on a system, whether this is wind or traffic, for example. So we have to deal with the fact that there's no precise information on the loading in most realistic settings. We have some structural information a priori, but this can be uncertain. Oftentimes we are discussing parametric uncertainty, but in many cases it can also be model form uncertainty. I will refer to this later. And we would like to extract the response of the system, the output, as I said before, in the full field feasibly, so also in unmeasured locations. And the reason we want to do this is because we want to have the possibility to develop prognostic indicators, for example, to assess the fatigue accumulation of the system under the already experienced but also future acting loads. And so to do this, we need to be able to predict the response even in unmeasured critical possible locations that are not always easy to instrument. The challenges that come with this task is, of course, the uncertainty that I mentioned in multiple aspects of this flow chart already. The fact that we can deal with systems that are nonlinear, which means they are more challenging to simulate. The fact that our observations or measurements are sparse. And the fact that we can be dealing with large dimensional systems, and this is especially the case for large-scale civil structures that can be complex. I'm going to show you first how to deal with the aspect of large dimensionality, because this is a critical aspect of hybrid modeling. As I said in the beginning, we need to develop models that can compute fast, and this is not usually the case for most of our numerical models, If you think of your typical finite element-based approximation, then this often takes hours to compute, especially if we're discussing nonlinear response, either due to geometric or material nonlinearities. So assuming you have such an expensive full order model, as I will call it, it is possible to reduce this kind of model, again, even if it is nonlinear. And one way to do this, and it has been exploited by different researchers in the recent years, is to use an autoencoder setup. The autoencoder is a neural network that brings down the original large dimension of the system to few or to a lower dimension of the latent space. And what we have done is to use this kind of logic and cast it inside a dynamic simulation. So we take the dynamic equation of motion of the system, but we express it in the latent space. Now we use an input force that is acting on this reduced space, and we use an integrator, as you would use, for example, your Newmark method in a conventional finite element setting. In this case, we use an LSTM, which is a recurrent neural network that integrates our system, meaning that it can predict the response of the system at the next point in time, but always now in this reduced space. The good thing with an autoencoder setup is, of course, that when using the function of the decoder, we can project back from this reduced space to the original dimensions of the system. So we can compute the response of our numerical model at the original dimension, and meaning the physical coordinates. This is very important for monitoring purposes, because what we measure and what we have to contrast against these predictions is at the physical space. It's quantities such as displacement, strains, or accelerations. So we have verified this framework both on simulations, but also on experimental data. You see here an application on a popular benchmark for the structural health monitoring community. This is the nonlinear benchmark of the Los Alamos shear frame, where there's a nonlinear bumper. This is the nonlinear element of this frame that induces a nonlinear response of the system. And we try to use this concept of the simulation using an autoencoder setup combined with the LSTM. We specifically use a variational autoencoder, and I will explain why this is. A variational autoencoder tries to enforce statistical independence on the latent space. And this means, or we show in a recent publication, that this ends up giving us a decomposition that approximates the so-called nonlinear normal modes of the system. So we have this logic of nonlinear normal modes, which, however, cannot be superimposed in a classical framework. But now, through the use of a variational autoencoder and through the decoder function, we have a representation that is invertible. This is very valuable because then we can simulate the response of the system, and we show that we get components that, when plotted in the spectral domain, are actually reflecting different modes of the system. Of course, this is a nonlinear system. You would never have a clear separation, but this is actually a quite successful decomposition here. If you were to use a more conventional decomposition, you would see that you would get mixed components, which ends up not being as efficient, or at least not so useful for the purpose of feature tracking, which is essential for monitoring. We have been using this approach in collaboration with Siemens Gamesa, again, for the purpose of wind turbine reduced order modeling, and specifically for the simulation of the nonlinear response of the soil for monopile foundation, where this autoencoder combined with an LSTM is actually trained on a physics-based model of the soil response that are described by such nonlinear PY curves, and which we can then reduce to generate the response of the system in all desired locations, and to do so in a much in an accelerated way. So at fragments of the computation of the original physics-based model. So this computes, in fact, in real time. Oh, okay, sorry, I could hear something, but hopefully not now. Okay, so let me show you, or before I show you how to go a step further, I show you here another implementation that we did on a benchmark that we have developed for the monitoring community. For those who develop reduced order models for nonlinear systems, we have a so-called nonlinear frame that we offer through the nonlinear benchmarks page, which you can actually look up or also retrieve from our website. It's a nonlinear frame of multiple degrees of freedom. All of the nodes are described by nonlinear joints that follow a bookend hysteretic type of behavior as the one that you see described here. And so we use this as a system of multiple degrees of freedom where we can experiment with the reduction. And we show that also this approach that I described here is very successful. In this case, again, giving you a real-time computation when the original system does not compute in real time. But where we fail with such an approach is that we cannot very easily express parametric dependence. There is a way to do this. You can use what is called a conditional variational autoencoder, which would allow you to condition the different parameters. But an aspect that is lost or is not so straightforward when using such an approach is that you cannot propagate uncertainty, or you can try, but in every step of the computation, the uncertainty would be increased. In order to better, therefore, define the problem for the cases where uncertain computation or parametric dependence plays a major role, we follow an alternative framework that again tries to achieve this kind of a reduction, but this time having a stronger physics-based connotation. In the previous case, we used the physics-based model, which we tried to reduce using the autoencoder, but we never explicitly used the nonlinear equation. In this second alternative, which is the so-called projection-based reduction, we actually tried to end up with a reduced equation of motion, a nonlinear equation of motion, which follows our original system. And so this is indeed what happens in this approach. And the way in which this is achieved is by using a projection basis, essentially a Galerkin projection basis, which when multiplied with the functions and matrices of our system allows us to extract a system or an equation of order R or dimension R, which is much lower than the dimension N, but at the same time still remains a structural equation of motion that can be solved with our conventional and very well-known rules. Now, the extra benefit of this projection basis is that it can be conditioned to account for parametric dependence. And parameters of the system can be the characteristics of the properties, the geometric and mechanical properties of the system, characteristics of the excitation, such as the spectral content and the amplitude of the excitation. And this allows us to develop these reduction bases through different regions of our parametric space. Effectively, this works in a sort of clustering approach. Let me show you here the logic. We have an original finite element model, which is our source that we want to reduce. We generate simulations from this full order high fidelity model for different sets of parameters that define the model. And we develop, we use a projection-based approach, essentially a POD, to develop these reduced bases, these matrices that then allow us to form this reduced equation of motion that we can solve and obtain the nonlinear dynamic response of the system, again, with the purpose of doing this in real time. Because I don't have much time, I won't go through too many of the details of this approach. I just want to explain that in our group, we have tried to improve the way in which parametric dependence can be expressed. And I'm just going to give you an example here. One very useful parametric dependence for engineering simulations is the parametrization of the input. And this relies on work that has been done by Rezan and Verkiregyan. And so they have already shown that earthquakes, for example, can be parameterized into a set of parameters that reflect the temporal and spectral characteristics of the signal. And this is, in fact, what we use here to break down a complex input, such as an earthquake, into a set of parameters. So if we can parameterize an earthquake, then it means that we can also develop models that are in accordance or that depend on these input parameters. What we have tried to do in order to express this dependence in a more efficient way is that we have intervened into this projection procedure. For those of you that are familiar with projection-based approaches, you know that we follow a projection on a manifold space that allow us to extract these different bases across the parametric domain. What we try to do is to have a second level of projection, to have a hyper compression in a sense, by projecting these bases and tying them to a global basis that can be used to regenerate in a more efficient way these reduction matrices for different sets of parameters of our system. Another way to do this is to use the autoencoder concept that I mentioned before, but now in specifically for these projection bases, so that we can again use these kind of physics-based reduced equations of motion. Again, I won't go into the details, but what I would like to show you here is for this same benchmark structure that where we have this parametric now dependence on, for example, the properties of the input excitation, such as the angle of the ground motion or the amplitude factor, but also dependence on characteristics of the structures, such as the Young's modulus, or even the hysteretic parameters or damage characteristics of the system. We can have a multi-parametric dependence in this case, and we can generate these reduced order models for these different realizations of the parametric vector. We can do this using different approaches. Here I'm showing you a comparison between a conventional approach and the one that we suggest on the basis of this use of or incorporation of variational autoencoder. Both of them achieve a speed up which in this case is about a factor of 10, which is enough for real time. What is interesting for us is that by using the second level of projection with the autoencoder, we also achieve a better approximation, so a lower error with respect to the conventional approach. What you see here in the first row is the reference, is what you would do, you would be able to do if you knew perfectly the basis that reconstructs the system, which is, however, never possible, because this would mean that you need to very densely train your model for an extended set of parametric vectors, which starts becoming infeasible or non-meaningful. So here we're showing this performance of the reduction of, or the increase in accuracy and precision for this modified approach. What is likely more interesting for those who are not familiar with these methods is the fact that you can reproduce the nonlinear response, and you can do this in the time domain. So you can do this for the full time history of the problem very successfully for both methods, a bit better for the method that we suggest. And additionally, when using this autoencoder type of approach, we're also able to deliver confidence intervals on our prediction. So you see here this feature where we not only yield the prediction of the system, of the dynamic response, but we also give the uncertainty bounds that comes with this prediction. This is something that could not so easily be done with the first approach of the LSTM and the autoencoder, but is now feasible due to the physics, the nature of the equation that we're solving and that we're maintaining with the projection-based approach. So now that I have discussed the reduction of dimensionality, I want to come to the aspect of fusion of the data with these reduced order models. And I mentioned in the beginning that one way to do this or to accomplish this is by using a Bayesian framework. And in my group, we have been working on these Kalman type of filters or Bayesian filters for a number of years. The main elements that characterize these filters are basically these two equations: the state equation of the system, meaning the equation of motion, which I showed can be a reduced equation of motion and can be parameterized, and the observation equation, which is really where data comes in, because this reflects the few and sparse observations that we have from our original monitored system. Now, this kind of synergy between the data and the physics equation can be accomplished using a Bayesian framework in two steps: the prediction step, where essentially we exploit the physics to predict the step ahead, and the update step, where essentially we exploit Bayes' theorem and the data to understand what is the correction that we need to enforce onto our prediction so that we get an improved posterior. Of course, this theoretical solution is cannot be achieved in the types of systems that we are dealing with, that are usually large dimensional but feasibly nonlinear systems. And so we result in the use of approximations. And one of the most typical types of approximations for such methods is the use of particle filters, or in some cases you may hear of unscented Kalman filters. And basically what these mean is that we try to approximate our state as a probabilistic, as a random variable, which can be approximated through the use of certain sampling points referred to as particles or sigma points if we're discussing the unscented Kalman filter, and which try to reflect the distribution of our state, for example, the displacement or velocity response of our system at time tk, which can then be propagated to the next point in time, k+1, using the physics of the problem, the equation of motion. This is our prediction step. This takes us to the next point in time, where again, these particles can be propagated even through nonlinear expressions. And this is the power of approximating these variables through such a sampling. And using the logic of our Bayesian update, we can then use the update step, meaning we can use these sample particles, propagate them through the measurement equation, understand what is the discrepancy between the prediction and the actual measurement, and use this to obtain a weighted improved posterior estimate of our state at the next point in time. This is the rough working of how these approximation methods are used. In our work, we have suggested through these last 12 years different types of approaches for such prediction for the purpose of only response, usually referred to as state estimation, for state parameter estimation, so for the case where both the response and some of the parameters of or the physics of the problem are unknown. For input state estimation, this is the case where you do not have information on inputs and loads, and combinations of these. So let me show you an example on this. Again, inspired from an aerospace structure. Here, in this case, we have a fuselage panel where we would like to predict the response of in different locations of the panel. For example, these green locations on the basis of few and sparse sensors. For example, accelerometer sensors here in these red locations. And what is more, we would like to also exploit physics to detect and predict damage in case this exists. And for this thin structure, the damage would, we assume, would be created in the form of different cracks throughout the panel. So to achieve this, we use a physics-based model, which is to some degree also computationally efficient. It's the extending finite element method that we use in this case, but it's in no case is it a real-time type of approach. So we utilize the previous logic of the projection-based methods. We generate different simulations from our system from different locations of the cracks. We need to also adopt a trick, let's call it in this case, to be able to achieve reduction. And the trick that we're using is mesh morphing. We use a reference crack and a fixed mesh, which we deform and distort in order to account for different possible locations of cracks, linear cracks throughout this system. And we try to do this both for flat and curved surfaces to reflect this fuselage geometry that we have here. At the end of the day, using this projection-based approach and the mesh morphing element, we can achieve a dynamic simulation of all of the degrees of freedom of this structure, and we can also achieve it in real time. This means that then we can use the Bayesian filtering logic that I mentioned before and combine the reduced order model, which is reflected in the top equation here, with the measurements that are obtained from the system in these four specific locations, under even the assumption of unknown input. Again, I won't go through the details here, but for those interested, you will find them in a recent publication of ours. And we can put them inside a Bayesian logic. So this is a representation of a particle filter. It's actually a bank of particle filters that can operate for unknown inputs. So they are specifically augmented Kalman filters, as we call them. And they are formulated for different parameter settings. And the parameters in this problem are really the positions and orientations of the possible cracks in this geometry. And so by using this Bayesian filtering logic, we can converge after an initial assumption, and as the algorithm progresses, to the actual location and orientation and length of this crack, or multiple cracks throughout our problem in this example. And quite importantly for us, we can also predict the response of the system in these unmeasured locations. We can do this quite successfully and in a dynamic fashion. And we can do this at only a fragment of the time of the original model. So an original model could be between 71 or 22 seconds, depending on the coarseness of the mesh and the size of the elements that are being used. But our reduced order model computes at only 0.12 seconds, again, for a simulation that is 20 seconds in total. So it's, of course, even lower than a real-time computation. So now we have shown that we can combine models and data, but I showed that in a Bayesian filtering setting, I can do this using an equation of motion, and this equation of motion should more or less capture the problem, or at least adequately capture the problem. But there exist a number of problems for which we do not necessarily have models that are accurate, and where we can actually have model form uncertainty. So it's not just the parameters of the model that are possibly uncertain or unknown, but it could be that we're missing part of the physics. Perhaps the damping mechanisms, for example, of the problem are not entirely known. Perhaps nonlinearities exist that we're unaware of, or we just simply do not know with great confidence what the model of our problem is. One of the situations where we encounter this problem is for the so-called problem of mobile sensing. This is something we use in recent project of ours. So it's the concept of using sensors on a vehicle, for example, a train, for assessing the infrastructure that is being traversed. And here you have to have an interacting model of the vehicle and the infrastructure, which oftentimes is not easy to compile. So this is what we're doing here in Singapore, where I am at the moment for this semester with our group here at the Future Resilient Systems Lab. We're developing a mobile sensing platform. It's essentially a very cheap sensor that can be deployed on the axle boxes of trains or on the chassis of vehicles, and which collects information, typically in the form of acceleration, that can be used for assessment of the underlying infrastructure. Here is now the concept that I mentioned before. How do we cope with the fact that possibly our models do not capture the full physics? Well, in this case, our suggestion is to still exploit the physics, the partial physics that we know, and to try to combine now two terms: a physics-guided term, which follows the logic that I showed up till now, and an additional term that can reflect the discrepancy between what we know and what the reality of the problem is, and that are essentially superimposed and fused to obtain the true behavior of the system. The reason why this is beneficial as opposed to using a black box approach is because even by fusing partial physics, it turns out that we can extract predictions that have a physical connotation that can be translated in the physical coordinates of our system, and which for us, for virtual sensing, is essential because we need to predict response that makes sense. I will show you directly an example of how we do that in this problem of mobile sensing. So imagine you have a vehicle that is traversing a roadway where we want to infer the roughness, so the profile of the road. We fuse the physics that we know, which is some sort of approximative and probably not completely accurate model of the vehicle, and and we leave a part to be learned by the data using a neural network that is to capture this discrepancy. I show you here how the combination of these two terms can lead to different types of results. So in this upper plot, you have a higher weighting of the physics, and in this lower plot, you have an equal weighting of physics and the learned term. It turns out that the optimal convergence or performance is obtained for a weighting that is in between these two options. And this is something that is, of course, for us also learned by the framework. This is something we're testing now on actual systems using a vehicle here by the the MIT Smart Lab here in Singapore that actually gave us access to this vehicle that we use as a test bed. Because I do not have much time, I would like to very swiftly show you what we can do after we have done these combinations. For those interested in our combination or fusion of machine learning models with physics, you can look at some of the recent work that comes from our group here in Singapore. You see here some of the main contributors. And so I will just go directly to this final section of what is next. We have shown that we can develop purely data-driven indicators, but mostly do diagnosis. We can now fuse physics to do more elaborate prognostic tasks. But how do we use this? So one way in which we would like to use these indicators comes from work that we're doing recently with TUM, with Daniel Straub and Anton Skamariotis. Where I missed one. Yeah, apologies for this. So here you should be able to see the flowchart that we're using for this concept, which is the value of information for structural health monitoring. But which you can see reflected in these plots, essentially we would like to quantify what would be the reduction in uncertainty that we can achieve when using a monitoring system that is deployed on our structures. And if feasibly, we would also like to quantify what's the monetary benefit of including or deploying such a monitoring system, and how can this be translated into gains that reflect the management of our system. In a next project, or a current project, which we're doing right now with the Swiss Federal Railways, we're using these indicators that come from the fusion of physics and data to drive or guide decision support in the sense of what would be the optimal action to take given such an indicator, and what could be the optimal observation to then take. Would it be a visual inspection? Would it be a non-destructive type of evaluation, something that is more pricey but more refined, so that I can navigate through the decisions on how to handle critical infrastructure. So we have shown this for the case of railway assets in an initiating work. We use the monitoring indicator that comes from mobile sensing, as I explained before. This is one such type of indicator, the so-called fractal values. They reflect the condition of the track. And on the basis of these fractal values, we can guide the decision as to how to intervene to do a medium, a moderate repair, or a replacement of the track that is more substantial, so that we can minimize the costs over a certain horizon, a management period of the railway track assets. So with this, I would like to conclude. I'll just leave you with the idea that we're trying to promote, which is the use of what others would call a gray box approach, or I prefer to refer to as a hybrid modeling approach, where the physics can be used to boost our learning and to guide more interpretable decisions for our assets. So with the members of the group that have contributed to this work, I would like to close this presentation and receive any questions. Thank you very much.
Yeah, thank you very much for this nice and also, I think, rich content, this presentation. I think it's amazing, honestly. It's full of content and interesting topics.
Yes, I tried to show all of the aspects of the chain. And I might have taken a bit more time than I should have. Apologies about that. But it was important for me to show the whole story, let's say, of how this evolves.
This is successful in the nice groups, I think. Yeah, I'm sure there are many, many questions, I'm sure. Yeah. Now it's time for, if you have any questions, it's a good chance. Maybe people, I think maybe I start. And may I ask one thing? I saw you mentioned in the middle part, you have a very long time talks about, you spend a long time talks about this
reduction, right?
The model to reduce the dimension, or reduce the Yeah, what's the
model order reduction? Indeed, to reduce
model order reduction. Yeah, model order reduction. I just
to essentially accelerate the computation.
Yeah. Just interested because is it possible that my question maybe you already talked about, but maybe I miss it in your presentation, that is it useful or can it use directly to support the decision SHM, like health monitoring?
Because actually what I would, the reason why I dedicate a large chunk of the presentation to these reduction approaches is because they are a necessary tool, but they are not sufficient. Model order reduction is the tool that we use to bring down the computation to a point where it's feasible for us to run the model in tandem with the data, so on the fly as data is attained. If you're not pressed for such, if you're not pressed for time, so if you have all the time in the world to do a prediction, you do not need to use a reduction approach, of course. You could dedicate hours and hours or parallel processors to try and run your original full order models. So reduction, in my opinion, or in what I try to show here, is not a direct means to decision support, is only one of the necessary elements for decision support. The reason why reduction further to this real-time feature is, in my opinion, useful, is because it also offers this means to parameterization, parametric dependence. So you can have multiple realizations from a model for different types of parametric sets that reflect either loads or properties of the system, and you can have the output in a almost, let's say, with a very affordable computation. So it's not only useful for real-time diagnostics, it's also useful for uncertainty quantification tasks, because essentially you have a surrogate to your system that can be materialized or can give a result over different parametric combinations, or different sets of parameters to your problem.
Yeah, thanks. There's one. Thank you very much. And there's no, not only one. There was several questions from the chat box. I was can these people can direct read, or can I?
Yes, maybe I can.
No, I will read it. It was a nice presentation and explanation. I would like to know that how could we use the collaborative approach from machine learning and physics-based models to improve the precision in structural behavior predictions, and finally to improve our codal provisions based on its inputs.
Right. So the reason why in our recent works we moved away from a traditional Bayesian framework, which really is more strict in its composition. This traditional, at least the Bayesian filtering frameworks that we use, heavily rely on the presence of an equation of the system, the so-called state equation. And usually this has to be formulated in a very explicit manner. And the only freedom, let's say, we have there is to assume that maybe some of the parameters of the model can be uncertain, or maybe there is some noise or uncertainty of the model that can be encapsulated, usually in a white noise type of assumption. But we found that oftentimes this is not enough, especially for systems that are as ill-defined as these mobile sensing problems. So again, where you have a system for which you don't have a precise model, imagine a bridge. This bridge is being traversed by a vehicle or different vehicles that carry sensors, and you would like to try and use some model of the bridge, which is not perfectly known, and some model of this vehicle to try and get the best possible approximation. So what happens in this case is that you have to account also for a discrepancy in the form, in the assumed form of the model. And oftentimes in practice, at least for us, this uncertainty comes from dissipation mechanisms that are never very precisely defined, or friction phenomena, but also from nonlinear effects that are also not very adequately understood or represented. And so this means that in this case, we need to leave some slack for the learning. And this is why we try to combine this approach of the Bayesian filtering framework, but now in a deep learning setting. Specifically, we use a deep Markov model in the approach that I showed. But contrary to what is done in the literature so far, instead of using this deep Markov model as a black box, so everything is learned by neural networks, we try to force in the transition dynamics the physics of the problem, much like our conventional previous framework. And we found that this is tremendously beneficial, even if you don't know the full, even if your model is only partially accurate or partially correct, this is still beneficial because it allows us to deliver predictions that have a physics connotation. They are displacements and accelerations of the physical space, and even now that we have the power of the model, even in degrees of freedom that are not being measured. So this was the strength that came from this fusion. So yes, to reply to this question, I do think that we can improve accuracy in this way because we have a better way to reflect discrepancy. But now to the question on caudal provisions, I assume that based on caudal, when the term caudal provisions is used, we're discussing standards and equations that can be delivered to practitioners and on the basis of which they can take their decisions. And I think that in this case, we cannot escape the task of having to fit again an interpretable model on these neural networks. And actually, we have done work on this. So even when you use let's say when you use a neural network to learn what we do not know with physics, it is possible to fit interpretable functions, so known functional bases on these neural networks. For example, using sparse approximation, using the SIMD logic for those that are familiar with nonlinear identification, and extract an approximative and analytical model that can fit this learned black box. So in that case, yes, I think also the second part of your question is possible. By doing this kind of fitting or sparse regression on the learned function, you can actually recover probably meaningful models that can be used by engineers also for design. I hope this replies to the question. I'm sorry for the long-winded reply, but it's hard to describe the whole framework in just a few sentences, so I hope it's understood.
Yes, another question from Agis Agasoliklis. Maybe I read it. I think it's excellent work and as always, and nice presentation. And one quick question is, how do you encode the environmental forces that you apply to the room? For example, in an offshore wind turbine, how do you deal with wave and the wind forces applied to the encoded room?
Yes, this is a very good question, and I couldn't also include this example in this case. I did show it, for instance, for the case of earthquake, where I showed that you can assume that the earthquake is parameterized on the basis of these temporal and spectral parameters that describe the characteristics of a specific earthquake input. But in that case, you need to be measuring that earthquake force. The problem with wind excitation and wave excitation is that most of the time we cannot measure it. And this means that we have to make assumptions for it. And that's where we use these input state estimators. These are basically filters where we use an evolution model for the input loads. For example, a popular assumption, which works specifically for wind, because we have implemented it for wind turbines very frequently, is a random walk model for the wind excitation. If for any reason you assume that the wind is a realization of a specific spectrum, you can also use this as an evolution model. You can put it in the assumed state space equation. A more recent work that we did that accounts for monopiles that have both wind and wave loading uses Gaussian, a spatial-temporal Kalman filter, which basically means a kriging model together with a Bayesian filter. The kriging model is used to account for the distributed loading of the wind and the waves. The Kalman filter and the random evolution assumption accounts for these unknown inputs, which are actually inferred together with the responses. But again, we need to have measurements or specific measurements that will help us achieve this inference. I don't know if this was clear. I can forward more information about this. This is actually work that will be presented in the next IMAC conference for those that are interested this February.
Yeah, there's another question comes out. Thank you very much, Professor Kathy. That's an impressive presentation. Is it possible to obtain the analytical response of a strong nonlinear multi-degree system under harmonic excitation? Do you have any suggestion or reference?
Well, the analytical response of a strongly nonlinear and multi-degree of freedom system is not easy to extract. You can use approximative methods such as the harmonic balance method, for instance, and there exist toolkits for doing something like this. But in fact, this is what we're trying to avoid in this work. So we're trying to avoid having to compute something in an analytical form, but instead we try to approximate it using these surrogates, either the LSTM and autoencoder surrogate, or these projection-based surrogates that come from numerical simulations. They come from so-called snapshots, meaning from runs, simulations of a full order model. I can forward you references for both, but the argument I'm trying to make is that it's more efficient to go for the approximation rather than the analytical representation of such a system.
Yeah, I saw some people comments on the Chinese website that he said that it's one professor in Beijing. He said it's the most beautiful and most nice academic presentation he ever saw.
Yes. Thank you.
From Beijing,
thank you for the comment.
University of in one university in Beijing. Yes. Any more questions? Yes. If not, we can talk later about further. We can further communicate, but I think it's already very late in Singapore. Yes, thank you, Helene, for your time.
It's not a problem. It's always a pleasure, and thank you for the very nice questions. For those, because I did show a lot of material, but of course, again, this is because I want to show all of the components of really a framework that has to go from end to end, from data acquisition to parameterized system assessment. If you have specific questions and you would like more resources or even the papers where these examples are taken from, please feel free to email me and I will reply and forward you all of the details and references that can be used.
Yes.
I also want to say that we have, for many of these methods, including for the methods that are on the physics-guided machine learning approaches, we have code that we make available together with the paper. So please contact me and I will also send you the codes that are completely open access, open source.
Yes, thank you, Mitchell. I think it's also very interesting for me, actually. I hope to contact you as soon as possible about many things here. Thank you.
Thanks very much, Arjun, for the invitation.
Yes, thank you. If it's no more questions, maybe we close now, Professor Lee, if you have anything to talk.
I don't have any question. Thank you again.
Thank you. Have a nice night.
Yeah.
You too, yes.
Bye. Bye-bye.
Bye.
Bye.